So our first example is objective number 7 in Unit 2, and it's called the product rule of exponents. This particular example also happens to include some negative exponents along the way, so we'll need to know how to handle those as well. But the giveaway here is that what we're going to be doing in this problem is multiplying. So the word product there is your key word to know that what we're doing ultimately is multiplying. But we're not multiplying exponents, we're multiplying powers. In other words, we're multiplying things like u to the 7th multiplied by u to the -1. So that's where the multiplication is happening. Any change in that operation at the level of the exponents will happen upstairs with those numbers, 7 and -1 and so forth. So let's try and lay out a strategy. Strategy in this problem is again to do what we did previously, which is we want to take any operation which is happening to a power. In this example, we see multiplication of powers happening. And we want to convert that into an operation that happens to the exponents upstairs instead. And on the arithmetic layer cake, what that means is that that operation of multiplication is going to move one layer down when it goes from the power to the exponent. And it's going to become, instead of multiplication, addition instead. And the first step, again, I like to say, is to find the powers. So where are all the powers happening? Let's make all the arithmetic that makes up this big expression that they've given us here. Let's make it all explicit so that we can see it. It's out in the open and we don't miss anything. So in order to find the powers, again, remember the order of operations. Remember PEMDAS. And what PEMDAS means for us here, since we don't have any parentheses, is that all the exponents happen before any of the multiplication happens, which means that an exponent such as that -2, which is up there by the x, that exponent applies to the x and not to anything else that comes before it. It also means, for example, that the coefficients, the 2's, the 7's, the 4's, and stuff that we see in this problem, that those are not, in fact, being raised to any power at all, because they're just multiplying into those expressions, which happens after the exponentiation does. So let's make it all explicit. Here are the powers that I see. I've got a v by itself. I've got x to the power -2. I've got v to the power -1, u to the power 7, u to the power -1, and x to the power -4. So I've got a total of 6 different power expressions going on in this big list. And what I like to do now is to rearrange the product. Now, first of all, why do we get away with this? We can get away with rearranging multiplication because multiplication doesn't care, at least the answer of a multiplication problem doesn't depend on whether you multiply in one order, whether you multiply in another order. So I can rearrange all these factors. It's called the commutative property of multiplication, and still end up with an expression that's equivalent to the original. And so what I'll do is rearrange it to put like factors together. Like factors is a term you may not have heard before, but I like to use the term to indicate that these are powers that have the same base. So all of my powers of x I want to put together. All of my powers of v I want to put together. All my powers of u I want to put together. And all the numerical coefficients that don't have any variables in them, I want to put those together as well. So first, the numerical factors, the coefficients, the 2, the 7, and the 4. Let's put those up in the front, typically where coefficients go. Next, let's look at the powers of u, and we'll stick those powers of u together. Again, I'm not doing any arithmetic here. I'm just rearranging, and taking this additional step in your work can sometimes help you to make the wrong, not to make the wrong type of arithmetic operation later on. So I'll put the powers of u together. I'll rearrange the powers of v to put them together, and I'll rearrange the powers of x to put those powers of x together. So far, so good, right? All we've done is rearrange the factors that are present inside of this problem. Our new expression is still equivalent to our old one, but what's nice about it is now we can see the path ahead of us. The path ahead of us is we're going to be able to combine those powers of u that are written in orange together by doing something to their exponents. Same thing with the powers of v, same thing with the powers of x. So there's that. Here comes the next step. Before we move to that next step, let's look for any hidden exponents. And in this example, there's one place where there's an exponent that we're not currently writing. So let's make it completely explicit. That v, which is just by itself, the first power of v that's listed there, let's give it an exponent of 1, just to remind ourselves that that's 1 power of v. So there is actually a secret exponent up there that we're going to need to remember in just a moment. Now we can finally move on to multiply these powers. How do we know we're multiplying powers? Well, look at all the multiplication signs that are on that row. The 2 powers of u that we have listed here are being multiplied by one another. The powers of v are being multiplied. The powers of x are being multiplied. And according to the arithmetic layer cake, if I want to multiply powers by doing something to their exponents, that something had better be addition. So how do you multiply powers? You add their exponents. So just recopying what we have here. Let's take the powers of u, the powers of v, and the powers of x and escalate that multiplication to the powers up into the exponents where it becomes addition instead. So to simplify this big long product, what we're really going to be doing is adding the exponent 7 and -1 on the u's, adding the exponent 1 and -1 on the v's, and adding the exponent -2 and -4 on the x's. Well, 7 plus -1 is 6, so in total we have 6 powers of u. 1 plus -1 is 0, so in total we have no powers of v. We'll talk about what that means in a moment. And -2 plus -4 is going to give me a total of -6 powers of x. And again, we'll talk about what that means in just a moment. But that was the important new step in this problem. All of our arithmetic is now done for this problem because we've escalated all our arithmetic up into the exponents. The 2, the 7, and the 4, those just get multiplied like numbers multiply. We get a total of 56. So now all of the tricky bits are done, and it's just a matter of cleaning up our answer a little bit. And to clean up our answer, I first want to focus in on the negative exponent that we see in the x to the -6. Well, we know based on our previous video what to do with a negative exponent. Negative exponent just means to trade multiplication for division instead. Take that power and either move it from a numerator to a denominator or vice versa from a denominator to a numerator, depending on where it originates. So for x to the -6, what I'm going to do to change that minus into a plus is I'm going to change the multiplication in front of it into a division instead. That's all there is to it. And so in total, we're going to get divided by x to the 6th out at the end. Now, what about that v to the power of 0? There's not much of a mystery to a 0th power of something, although it's another very common place to forget what you're doing. Taking the 0th power of any non-zero quantity is really saying we're not going to have any powers, any factors of this quantity in our answer at all. It means we're not going to be multiplying by any v's, in short. And to not multiply by any v's is the same as to multiply by the number 1. So v to the 0th power, we're just going to rewrite that as the number 1. The variable v disappears because there are no factors of it remaining. So to completely simplify this, we're just going to make it easier on the eyes by not writing that multiplication by 1 explicitly, and also by taking that division sign, which is again kind of old and outdated, and turning it into a fraction bar instead. That has the effect of moving the x to the power 6 into the denominator, giving our final answer the form 56u to the 6th divided by x to the 6th. So what did we do here in this example? We wanted to use the product rule of exponents, and we knew it was going to be the product rule of exponents, not only because it said so in the title, but also because in the expression, we're multiplying a bunch of powers together. Some of them were powers of u, some of them were powers of v, some of them were powers of x. Those like factors, powers of a common base, when you multiply them, can be combined by adding their exponents. So all we did was go through and look for the exponents on the powers of u, 7 and -1, and add them together to get 6. The exponents on the powers of v, 1 and -1, added together to give us 0. And the exponents on the powers of x, -2 and -4, added together to give us 6. And so we knew in our final answer we would have 6 powers of u, 0 powers of v, and -6 powers of x. And from there, it's just a matter of simplification. The 0th power of v makes that factor disappear from our product completely, and the -6 power of x takes that x to the 6th and moves it into a denominator instead of a numerator. Most important takeaway again from this is that when you multiply powers, you can instead add